So let us start today's session. Hello and welcome to this NPTL TA session on heat transfer course. And today is week 12, and we will be discussing some questions related to week 12's course content. Okay. And my name is Amaan Dash, and I'm a research scholar from IIT Kharagpur. And we'll be discussing some problems related to uh, mostly radiation. Okay. So let's start with the first question. So I'll encourage you to try these questions on your own and then we can discuss the solutions. So let me first write down the first question and then I can tell you what the question is. Okay. So it is given that uh, so this is a cubical enclosure. Okay. And we have a spherical tank of diameter 2 meter. So so this is a spherical tank. Spherical tank. And the diameter of this tank is 2 meter. And this is filled with liquid nitrogen. Okay. So, and this is maintained at a temperature of 100 Kelvin. And this is kept in an evacuated cubic enclosure. So this is the cubic enclosure. And the sides of this cubic enclosure are 3 meter long. So these are all 3 meters long. The emissivity of the spherical tank and the enclosures are given. So let me write. So emissivity of the spherical tank. So let me say epsilon 1 for the spherical tank. This is given to be zero point 0.1, and we have emissivity of the enclosure equal to 0.8. Now, if the temperature of the cubic enclosure is measured to be 250 Kelvin, that means this enclosure is maintained at 240 Kelvin. Determine net rate of radiation heat transfer to the liquid nitrogen. The liquid nitrogen. So you know you have to use equation for radiation. So you can consider the Stephen Boltzmann constant to be 5.67 times of 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. And you can take certain assumptions like it's a steady state operating condition. So let me write those as well. Assumptions. One is steady state condition. So we have steady state operating condition. Then we have surfaces are opaque, diffuse, and gray. And there is no convection. Convection is, let's say, not considered. So you have to work only with radiation. And we have thermal resistance of the tank are negligible. So these are all the assumptions. So you can give it a try on how to solve this question, and then we can move on to discuss the solution. Okay, so let us try to solve this. Okay. So if we see this figure, we have a cubical enclosure which is at 240 Kelvin, and we have a spherical tank, and this is at a temperature of 100 Kelvin. So this is at 100 Kelvin, and this has a emissivity of zero point 0.1. So this is epsilon 1, that is zero point 0.1, and this cubical enclosure has a emissivity, let's say epsilon 2 is equal to zero point 0.8, and this is 3 meter long. So we have to determine the net rate of radiation transfer to the liquid nitrogen. Okay, so we have to find net rate of radiation, that is q dot, let's say, and from that we have to find from 2 to 1, that is to the liquid nitrogen, because liquid nitrogen is system 1. Okay. Okay. Now, if you see, uh, if we have to find out q2 to 1, one thing we can see is that this is a spherical tank. Therefore, if we see what is the net rate of radiation heat transfer from the liquid nitrogen, that is N2, you see all the radiations that are emitted from the spherical tank will be coming to the sphere, and none of the radiation that is emitted by this spherical tank will be coming back to itself, because it is a, you see, it is a convex surface. So everything will be going out, nothing will be striking back to the spherical tank. So if we want to find out q dot 2 to 1, that will be exactly equal to minus times of q dot 1 to 2. Okay, so this is a simple simplification we can do to easily calculate what is the net rate of radiation transfer to the liquid nitrogen. Okay, because we know that if we see from F, from system 1 to 2, that is all the fraction of energy that is emitted by surface 1, and that is coming to surface 2 will be 1. Okay, because all the radiations that are coming out of surface 1 will be intercepted by the surface 2, and this we can easily calculate by, you know, network method or resistance based method for this radiation transfer. So that is nothing but we can write, uh, so this is from 1 to 2 we can write a1, then we have sigma t1 to the power of 4 minus t2 to the power of 4. But since we have different emissivities now, so we have to divide it with respective emissivities, or okay. So for system 1 we can write that will be 1 by epsilon 1. Okay, and then for system 2, when it will be coming to surface 2, we will be having 1 minus epsilon 2 divided by epsilon 2 times of A2 by A1 by A2. Okay. Because we have taken this A1 to the top. From here, A1, if it will be there, epsilon 1 A1, then I have taken it common and taken to the numerator. So this will be A1 by A2. Okay. So first we have to calculate A1 and A2. So A1 is the surface area of the sphere. So this is okay. So we have pi d square, that is equal to pi. We have diameter given to be 2 meters. So 2 square. So we can write 4 pi. And similarly, A2 is equal to 6 times of A square, which is nothing but A is 3 meters. Right? So we have 6 times of 3 square. And all the emissivities values are given, and temperature values are also given in Kelvin. So we can substitute all the values. So let me write. So we have Q dot 221 is equal to, we have A1, that is 4 pi. Then we have sigma, that is 5.67 times of 10 to the power of minus 8. Then we have T1 to the power 4. T1 is maintained at 100 Kelvin. So we have 100 to the power of 4 minus 240 to the power of 4. This entire thing divided by, we have 1 by epsilon 1, that is zero point 0.1, 0.1 plus 1 minus epsilon 2, that is 0.8. So we have 0.8 divided by 0.8 times of A1 by A2, which is 4 pi divided by 6 times of 3 square. Okay. So if we do this, we will be getting, this will be equal to around 228 watts. Okay. So the net rate of radiation heat transfer to the liquid nitrogen will be around 228 watts. Okay. Okay. Now let's move on to the next question. So just let me do this. Okay. So let's move on to the next question. So here we have a thin aluminum sheet. Okay, let me draw. Some aluminum sheet we have. Say, So, like this, we have three aluminum sheets. Okay. So, this is say one. This is second aluminum. This one is, let's say, two, and this one is the third one. Okay. So let me write. So it is given. It given a thin aluminum sheet. Okay, with a emissivity of um, 0.15. So it is placed between two very large parallel plates. Okay. So a thin aluminum sheet. Uh, this is a thin aluminum sheet, and it is placed on both sides. Is placed between two very large parallel plates, and these parallel plates, they are maintained at different conditions that are, let me write. This one T1, this is maintained at 900 Kelvin, and T2 is maintained at 650 Kelvin. So this aluminum sheet is between two parallel plates, and they both have emissivity of, this one has a emissivity of, let's say, epsilon 1 as zero point 0.5, and this one has a emissivity of zero point 0.8. So let me write this as epsilon 3. Okay. So this is some kind of system that is given. Okay. So these are parallel plates. Okay. So it can be assumed that there is no heat loss to the surrounding. So assume no heat loss to the surrounding. As these plates are kept very close to each other. So this is, so plates are kept very close to each other. So that is because to reduce any kind of loss to the surrounding, to each other. And you can, so this is obviously a radiation question, so you can consider Stephen Boltzmann constant to be 5.67 times of 10 to the power of minus 8 watt per meter square Kelvin to the power 4. So this question has different parts. So we'll do it one by one. So the first part is determine the net rate of radiation heat transfer between the two plates per unit surface area of the plate. Okay. So let me write determine net rate of radiation heat transfer, net radiative heat transfer between two parallel plates, between two parallel plates per unit surface area of the plates. So that is watt per meter square. Your unit will be watt per meter square per unit surface area of the plates. So you can try this, and again we can try to solve this. So this is again you can use this uh, resistance based method for radiative heat transfer, and you can obtain the net radiative heat transfer between both the plates. So it will be coming in watt per meter square. So let me write this one. Okay, so let's see how to solve this question. So it is given that, let's say if we consider a steady state operation or steady condition, then the heat that is lost by this inner lining, this will be coming to the outer lining and will be lost from the outer lining. So the heat transfer from the inner lining through the shields will be equal to the heat loss from the outer lining to the surface, right? So let's write that so it will be easier. Say at steady condition, the heat that is lost from inner lining through the shield will be equal to the heat loss from the outer lining to the, so heat loss from the inner lining. So this is the inner lining, you can see. So all the heat that will be coming to the outer lining will be lost to the surrounding by radiation and convection. So both the heat transfer rate will be the same. Okay. That is what I am mentioning here. So I hope you understand. So at steady state, all the heat that is coming from the outer lining to from the inner lining to the outer lining will be lost to the surface or the surrounding. Okay. So I can write this as heat lost by outer lining to the surrounding. And this heat loss to the outer lining by surrounding, we know, is taking place by two heat transfer modes, that is radiation and convection. So this we can write it as QR, Q dot of radiation plus Q dot of convection. So we'll evaluate it individually. So let's start with Q dot of convection. So this is equal to nothing but the heat transfer coefficient times uh, area, but will not consider area here. We'll consider per unit surface area. So this heat transfer per unit surface area will be considering. Okay. So we can write it as H times of T surrounding minus T, let's say outer line OL. Now H we can calculate from the empirical correlation that is given here 1.44 1.44 times of delta T to the power of 0.33. So that's 1.44. So delta T will be it is given the air temperature is 25 and outer lining is 100. So 100 minus 25. We have 100 minus 25 to the power of 0.33. So this will be nothing. We can write it as 1.44 times of 75 to the power of 0.33. So now we can calculate Q dot from convection. So Q dot of convection is equal to 1.44 times of 75 to the power of 0.33, and this Ts minus To is again same as that of 100 minus 25. So this is 5.99 watt per meter square. Okay, so this will be, this is 5.9 times of, this is 75. So we will be getting this to be 449.25 watt. So area, let's say area is nothing but 1 meter square, we can consider per meter square area. Okay. So this Q dot of convection we have calculated. Now we have another term, that is Q dot of R, that is heat loss by radiation. So let us calculate that as well. So Q dot of R is nothing but, we have emissivity epsilon times of A times sigma times of Ts to the power of 4 minus POL to the, actually I have written it wrong. This is outer lining minus the surface temperature. eh, Surrounding temperature. So we have OL and this is surrounding. So this is OL and this is the surrounding to the power of 4. So area as we have considered is to be 1 and emissivity is 0.87. So we can write 0.87 times of 5.67 to the power of 10 to the power of minus 8. And temperature we have to convert into Kelvin and then we can substitute it. So we have plus 273. So we don't need this temperature, right? We need 125. So 100 is 373. So we have 373 to the power of 4 minus 25. That will be coming to be 298 to the power of 4. Okay. So if we substitute all the values, we will be getting this to be 565.8 watt. So first thing you can notice here is that for both radiative and the convective heat transfer, you see this is the convective heat transfer and this is the radiative heat transfer. They are of nearly the same magnitude. That means they are comparable. So we cannot neglect one with respect to other. So we have to keep both the terms. Let's say sometimes we neglect the heat transfer rate due to convection because sometimes they are very, very less. But here we cannot neglect that because they are of the nearly the same or in value. Okay, so now we can calculate the total heat loss from the outer surrounding. That is, let me write Q dot total or is equal to, we can write 449.25 plus we have 565.8. So that will be around 1055 watt. Okay. So this is the net heat transfer that is lost from the surrounding, and that will be same as amount of heat from the inner lining to the outer lining. Now you see, if you see the first question, you see how we have done here is we have calculated 1 by emissivity plus minus emissivity of the shield or the second part as A1 by A2. But one thing you can see here, here A1, A2, everything, all the areas are same. And the two factor terms are also 1 because they are all flat surfaces. So, okay, let me write. So, all the view factor terms, that is uh, F1 to 2, then we have F2 to 3, all the view factor terms that we will be having, they're all equal and will be equal to 1. Okay. Another thing, let me write expression so that it will be easier to modify this. I'll tell you how to easily remember this expression. Okay. Now, okay. So if you see, we have to modify this for n number of sheets that we have. Okay. Now, if you think about it, you see, this 1 by epsilon 1 term, and here we have 1 by epsilon 2 and epsilon 2, but here all the epsilons are the same. So that is one simplification we can do. And all the areas equal, so we can just cancel this term. Now the additional things what we can do is, you see, this term 1 by epsilon that we have, if you think that there are n shields, say consider one shield. You see, it will be interacting with n minus 1 more shields. So if there are n shields, this one shield will be interacting with n minus 1 shield. Plus again we have two linings. So plus 2. So total we have n plus 1 interactions. Correct. So this 1 minus epsilon term that we have, so every shield will be interacting with n plus 1 n plus 1 times, because every shield if we consider it will be having total n plus 1. So we have multiply this with n plus 1 and again multiply with 2 because we have two sides of the shield. Okay. Now the next is, uh, here this one, instead of 1 by epsilon we will be having total n plus 1 such interactions. Okay. So you can see this is an easy way to remember, but how to derive it, you can see the lecture slides or the recorded video lectures to understand how we got into this particular expression. But this is a simple way to remember this. So this will be equal to the net heat transfer that we have, that is Q dot of total. And this area term we will be not having here. Okay. And if we substitute these values, this epsilon value, let me substitute it. So this is especially this part I'm doing, this part. So this is nothing but 1 minus epsilon is 0.87 divided by 0.87. So this is equal to 0.1. So if you do this, so you will be getting the expression to be something like this. Uh, yes, if you include this 2 as well. So this will be 0.0 divided by 2. So this will be simplified to 0.15. So now you can substitute the values. So this is equal to, we have 5.67 times of 10 to the power of minus 8. And this T1, now we have 773 because we have 500 degrees Celsius. So plus 273. So that is 773 to the power 4 minus, we have 100. That is, we have 373 to the power of 4. So this entire thing divided by, we can simply write it as, uh, this is n plus 1. So we have 0.15 plus 1. So 1.15 times of n plus 1. Because we have to find out the value of n. And this q dot also we know from previously, we have calculated this q dot. This total, we have calculated this to be 0.0155. This is, sorry, 10551. So from here and from, if you solve this, you will be getting, this implies we will be getting n that we have is equal to 15.78, and this will be minus 1. So that is around 14.78. So which is close to 15. So we will be having in total 15 sheets to maintain the outer temperature at 100 degrees Celsius. Okay, so so let's do one more question before closing this session. So consider a cylindrical furnace. Okay, let me draw. So we have a cylindrical furnace. And this has a radius is equal to height is equal to 1 meter. So the radius and the height we have, I'm drawing it here. Okay, the height. They both are equal. Okay. this is the radius and this is the height h, and radius being say r0. So we have r0 is equal to h is equal to 1 meter. The top surface, so let us give names. This is surface 1 and this is, let's say, surface 2, and this is surface. Okay, so this is surface 3 and this is surface 1, this is surface 2. So the top and the bottom surface has emissivity of zero point 0.8. So the top surface has the emissivity of, let's say, epsilon 1 is equal to 0.8, and the bottom surface has a emissivity of epsilon 2 is equal to 0.4. And this one is maintained at a temperature of 700 Kelvin, and the bottom is maintained at a temperature of 500 Kelvin. And this side, the third surface, it is this third surface, surface 3, closely approximates a black body, and it is maintained at a temperature of 400 Kelvin. So here also you can assume, there will be assumptions. So assume that it is a steady operating condition. We have steady operating condition, and the surfaces are opaque. Surfaces are opaque, diffuse and diffuse and gray, and there is no convection heat transfer. No convection heat transfer. And it is given that F1 to 2 is 0.38, and as usual the Stephen Boltzmann constant is 5.67 times of 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. So first thing you have to do is, the first bit of the question is the simple part. What will be F2 to 1 and what will be F2 to 3? So let me solve this question, because this is again a direct question. So we'll try to solve this straightforward. So let's see. So for we can write here 1 to 2 is given. So let me write F11 plus F12 plus F13 is equal to 1. That is, the total fraction equal to 1.
Now, if you see surface 1, it is a flat surface. So all the radiations that are coming out will be going to 2 and 3, and nothing will be bouncing back to 1. F11 will be equal to 0. Okay. And F12, this is given to be 0.38. So we can write F13 is equal to 1 minus 0.38. So this will be equal to 0.62. So this is F13. Now from 13 we can calculate. Now if you see from 1 to 3 what we have, first thing you can see 1 and 2 are symmetric surfaces. Like how 1 will be behaving, 2 will be behaving in the exact same way. Okay. So from that one, from that information we can actually calculate 2 to 1, right? Because if you see from 1 to 2 what we will be having, from 2 to 1 exactly same amount of radiation we will be having. So if 2 to 1 will be same as if 1 to 2, and that will be equal to 0.38. So we have done with this part. If 2 to 1 we have done. For F2 to 3 we will have to do this. Now from F2 to 3 is same as F1 to 3. So let me write that. We have F2 to 3 is same as F1 to 3, and F1 to 3 is 0.62. From here this is 0.62. Okay. So 2 to 3 also we are done. Okay. So this is also done. Now the second part of the question that is given is, what is F3 to 1? So in a similar way, we know F1 to 3, so we can calculate F3 to 1. So we have F3 to 1, A3 will be equal to F1 to 3, A1. So this implies F3 to 1 is equal to F1 to 3, A1 by A3. So this will be equal to 0.62 times of A1 by A3. So we have to calculate A1 and A3. So A1 is circular. So we have pi r square. Better if we write pi r0 square. Okay. And we have A3 is equal to, that is the curved surface area, is 2 pi rh. So we have 2 pi r0 times of h. And R0 is same as H as 1 meter. So we can write it as pi times of 1 square. So that is nothing but pi. And here also we can write 2 pi times of 1 times of 1. So this is nothing but 2 pi. So A1 by A3 is equal to pi by 2 pi, which is equal to zero point 0.5. So if we substitute this in here, we will be getting A31 is equal to 0.62 times of 0.5, which is nothing but 0.31. And now we have the last part of the question, that is what is the last two part of the question, that is what is the value of radiosity for surface 1, that is determine the radiosity of, that is we can say J1 of surface 1. So for that, we have to do the net balance of heat transfer. So that we can do. So let's start one by one. Like for the top surface, for surface 1, we can write sigma T to the power 4 is equal to J1 plus 1 minus epsilon 1 divided by epsilon 1 times of view factor F1 to 2. We have J1 minus J2 plus F1 to 3, J1 minus J3. Similarly, for surface 2, we can write sigma T2 to the power of is equal to J2 plus 1 minus epsilon 2 divided by epsilon 2. From 1 to 2, he will be having 2 to 1. We have J2 minus J1 plus F2 to 3. J2 minus J3. And the most interesting is the third part, that is surface 3. Why? Because it is a black body. Okay. So we can directly write sigma T3 to the power 4 is nothing but K3. There is no other term because there is the epsilon 3 is equal to 1. So all the right hand side except this will go to 0 since epsilon 3 is equal to 1. Okay. So J3 is nothing but sigma times of T3 to the power of 4. This is very, very easy to calculate. Okay. So it is given that determine the value of net rate of radiative heat transfer of surface 3. Okay. So J1 you can calculate easily. Uh, and by substituting this, you can also calculate. So wait, let me do one thing. You can actually try to get these values and then we can see how to do this. Now you have all the expression. So one thing you can calculate is, that is the fourth part that we have, that is determine the value of net rate of radiation heat transfer. Net rate of radiation heat transfer of surface 3. That is Q dot of 3. So since you have all the expression, you can easily calculate this. So let's do this. So if you see, this is nothing but we have 5.67 times of 10 to the power of minus 8, and this is T3. What is T3? 400 Kelvin. So we have 400 to the power of 4. So this we already know. Now uh, we can write for surface 1, we can write, let me write here, surface 1. So we have 5.67 times of 10 to the power of minus 8 times of T1 to the power 4, which is nothing but 700 Kelvin. So we have T1 to the power of 4. This is equal to J1 plus 1 minus epsilon 1, which is nothing but zero point 0.8. So we have zero point 0.8 divided by 0.8, and we have F12. So F12, if you see, is nothing but 0.38. So we have 0.38 times of J1 minus J2, J1 minus J2 plus F13, and F13 is 0.62. So we have 0.62. This is J1 minus J3. So J1 minus J3 is this much, that is 5.67 times of 10 to the power of minus 8 times of 400 to the power of 4. Correct? So let me copy this entire thing. And similarly, if I write for surface 2, instead of this 700, this will be T2, that is nothing but 500 Kelvin. So we have 500 to the power of 4. Instead of J1, we will be having J2. Instead of epsilon 1, we will be having epsilon 2, that is zero point 0.4. So this is 0.4, 0.4. And this will be F2 to 1. So I'm erasing this. And this will be this, I'm erasing this and this. Okay. So this will be J2 minus J1, and this will be J2. And here we will be having F2 to 1. What is F2 to 1? This is nothing but 0.38. So this is 0.38. And here we have F2 to 3. F2 to 3 is nothing but 0.62. So you have expression with J1 and J2. So if you solve both the expressions, you will be getting J1 and J2. So J1 is 11418 watt per meter square. J2 is nothing but 4562 watt per meter square. And J3, if you substitute the value, you will be getting 1452 watt per meter square. So now you have J1, J2, and J3. So J1 you have, sorry, J3 you have, J1 you have, and J2 also you have. So now you can calculate Q1, Q2, and Q3. So you can give it a try and then let me know. I'll let you know. So we can calculate Q1 dot, Q2 dot, and Q3 dot.